We already talked about why NumPy is faster than list. So here is an example. Look at here, we have a list of these integer numbers, and then we need to write a loop to square each element. So any computation that we do on elements in a list, we need a loop to go over all these items. But if we convert that list to NumPy array, that would be so much easier and we don't need any loop. So here we have our list that's equal to NumPy.array, our list. We convert this to NumPy array, and then we just need to write our list that's equal to our list and asterisk asterisk 2, which makes that which square each element in that array, and then we can see the result. So you've noticed that we don't need to write a loop to go over all the elements one by one. Let's have another example. Let's say we have a vector and we want to normalize it to be unit length. That involves dividing every element in the vector by a constant. That's the magnitude of the vector. So with list, we need to have a loop. This is our vector, and we have a variable magnitude that we initialize it by 0. Now, here, we need to have a loop to go through all the elements for calculating the magnitude. And then that's it. Now, for normalizing it, again, we need another loop, and we do our computation, and we have the result. Let's see if vectorized computation can help us in this way. We import NumPy as NP and NumPy.len algebra, that is the short form of linear algebra library, and we use it as NLA. Now we have our vector. See how we can convert this to a NumPy array by np.array.vector, and then how we normalize it, that's NLA.norm, using this function norm from this library and passing this NP vector to calculate the magnitude. And now we have it. See how the results are the same, but how we make it faster by using NumPy library. Then for normalizing it, we have this NP vector dividing by magnitude, and then new magnitude that's equal to NLA.norm. By using norm, we use this, and then we have normalized our vector, and we see the result, how this one is exactly equal to this one. But here you can see that we didn't use any loop. That makes our computation so much faster than using only list and loops. Here is another example to add two vectors together. As you can see, we don't need any loop here. Also, we can use it to multiply two vectors or two matrices like A and B. We have two matrices, and by using this operation, @ symbol, we can multiply these two matrices A and B together without using any loop.
So the first thing that's important to know is how to initialize an array. So we'll just say that A equals np.array, and then within this, we just basically pass in a list. So 1, 2, 3. This would be a one-dimensional array containing the values 1, 2, 3, as you see. And you can go ahead, if you're not using Jupyter Notebooks, and print A. Okay, cool. So we could also initialize a little bit more complex arrays. So we could do like a 2D array of floats, and I could do that the following way. We're going to have a list within a list. So here's some float values, and then we're going to make this two-dimensional. So here's some more float values. And let's go ahead and print B. Cool. So now that we know how to initialize arrays, and you can keep doing this, like I can nest list within a list within a list to create a three-dimensional array, etc. Some other useful things to know about this is how do you get the dimension of your NumPy arrays? So if I did a dot number dimensions, so this tells me that it's one dimensional for A, and if I did b dot and it would be 2. Shape is another important function, so get shape. If we do the first one, a dot shape, this is all we have to do. It's a vector, so it's only going to tell me the one dimension because it only has one dimension, so it's size 3. If I do b dot shape, it's going to tell me the rows and the columns. So this is 2 rows and 3 columns, so this should print out 2 by 3 as it does. Okay, other things, we want to know how much memory our NumPy arrays take up, so we can get the type and also get the size. So if we want to get the type, we do just a dot type. A dot data type int32 by default. So even though these are small values by default, it specifies that it should take up 4 bytes or be an int32. If we wanted to specify what type we wanted to store as, so maybe we knew that we didn't have any like big values, so we could do like an int16, and so that would take up less size, and you can see the difference in size in a sec. So right now it's int16, and if I want to see the size, there's a couple different, I guess, important functions with this. We can do a dot item size. So this should tell me 2 bytes, as it does. If we left this as an int32, it will tell me 4 bytes down here, as it does. You can also do, I think, the total size. I guess a dot size is the total number of elements. So the total size would be a dot size times a dot item size. Another way to do that is, I think, just number of bytes. As you see, that's the same thing. And you can also do this with B. It's like b dot item size. B's are floats, and I believe that this is an 8-byte type. So if I do b dot item size, as you see, yeah, it's 8. So floats are going to be bigger than integers usually, unless you define this as like int 64. And so yeah, I usually don't even worry about the data type too much. I don't